So when I was growing up, my father used to always call me an astute observer of the obvious. So I'm going to present this, and it may be obvious to all of you, but for me, getting into this field and ultimately starting my company 4 years ago, it wasn't so obvious to me at the time. So who am I and what do I do? So I run a company called Kyndi. We're venture backed. Some recognition that we've received. We're on the CB Insights AI 100 list. We're an innovator from IDC for their cognitive AI platforms, JMP Hot 100 software company. We're based in San Mateo. What I found interesting when I first got into this, and my background is in mathematics. I was a quant on Wall Street for 8 years, all through the financial crisis, which was awesome. I'm not kidding; it was super interesting. And when I got into AI and really trying to solve, and I say AI because we spoke a lot about machine learning. Machine learning is kind of one paradigm, giant bubble of artificial intelligence. And when I got into it, I had no idea about this entire other side of artificial intelligence called knowledge representation and reasoning. And what's super interesting now is that we have this big cycle around machine learning, and we've forgotten a lot about knowledge representation and reasoning. For example, I'm currently fundraising right now for the company. We're doing another round of our Series B. I had a venture capitalist email me the other day, and he said, so one of my co-founders launched the entire field of graph-based NLP with a paper back in 2004 with this student, Rada, I forget her last name, out of University of Michigan. The gentleman emailed me and he said, Ryan, graph-based NLP has been pursued since 2004, so your technique is old. And I emailed back, and he just funded a bunch of convolutional neural net companies, which I believe that paper goes back to 1989 with Jan LeCun, and those neural network techniques then all the way back to pre-Dartmouth conference, back to the early 50s and back to the 40s. So it's interesting. I always love to bring up this modern history of AI, because everything that we're doing now has actually been done for a very, very, very long time. I mean, the statistical techniques go all the way back to the 40s, go all the way back to the 50s. But then you have this paper from Marvin Minsky out of MIT called Perceptrons, where he essentially shows the limitations of these very shallow networks, forces them into a long AI winter, and symbolic artificial intelligence rises to the top and goes on until about 1985. And then you have Rummel, Hart, and Hinton come out with their paper on backpropagation in 1986, and now we're into this deep learning world. Actually, that deep learning really didn't start till AlexNet in 2012 when they started training their networks on GPUs. But I think it's important, and I hope everyone gets out of this, is go back and look at the history of your techniques. Because when I was, whether it was in finance or now in my company where we do, you can call it natural language processing, is all of these problems that you're likely trying to address have been attempted before with different techniques. So it was really important for me to go through this history of AI and understand, hey, if I'm trying to understand semantics of language or trying to parse sentences, it's probably been done before, and let's go back and look at all these different techniques and how people have actually used them. And what I came out of going through that history is I found that there was really two waves of commercialization in AI. And right now we're in this statistical machine learning. Everyone loves machine learning right now, and these systems are phenomenal at learning from data. They're actually not really good at reasoning. And you have these systems over here, these knowledge representation and reasoning systems, which didn't learn at all from data, were phenomenal at reasoning. And what's really interesting and what I'll show is at the bleeding edge of research right now, what you're seeing is the fusion of these techniques. And my whole purpose in kind of presenting today was giving my background in statistics, giving my background and everyone's background here in kind of machine learning and data scientists. There's an entire field of handcrafted knowledge techniques that you're likely not leveraging. And it'd be interesting to take a look at that. And what's really interesting is when I went through this history, I found that the reasons why these approaches really haven't been fused together even though they've actually been trying to do it for a while. But the camps actually hate each other. So what do I mean by that? So here's actually a comment on LinkedIn by a neural network researcher at Facebook. And he said, and this is the entire quote, quoting someone else, I believe he's quoting Max Planck, but I could be wrong here. This quote is probably a century old and yet so relevant for neural networks today until all or most of the go-fi's good old-fashioned AI people retire or die. I mean, it is incredible. I mean, when I went back through the history and going to conferences now with some of the older folks who've been doing it for a very long time, you still see this partisanship in these communities, which is really, really fascinating. But I believe that the future of AI and really the future of the techniques that you'll probably use if you start looking at particularly language data, actually even if you're looking at image data and other things, is actually the fusion of a bunch of these techniques. So bringing together, I say to solve any real business problem, you likely have to bring together 3 techniques: machine learning, knowledge representation and reasoning, and natural language processing. Just real quick, does anyone know what knowledge representation and reasoning is?
Nope.
Yeah, see, that's fantastic. So it's astute observation of the obvious, maybe isn't so obvious. And to give you an example of where this is going, so here's a quote from a paper in early 2018, from DeepMind, Google Brain, MIT, and University of Edinburgh. We reject the false choice between hand engineering, so your knowledge representation and reasoning techniques, these if-then rules, and end-to-end learning, so all the stuff that you're likely using, and instead advocate for an approach which benefits from their complementary strengths. And that's why we were profiled in the New York Times, is because we look at combining these approaches together very, very tightly, in the sense that you want to be able to machine learn from data, but then represent that network that you learn as a knowledge representation and then use it over. And what is the purpose? If I'm a KRR person, and we have a bunch of them at my organization, so if I'm an expert in knowledge representation and reasoning, why would I want to add machine learning or even look at machine learning? Well, one is to acquire the knowledge from the data. So if you're building your knowledge representation, a lot of times you would build those by hand. I mean, they're really, really challenging to build, very, very manual. So you want to be able to learn from data to construct your knowledge base. And the other one is to acquire knowledge from human beings. So the other thing, if you look back to the expert systems of the 80s, there was probably some knowledge engineer sitting with some subject matter expert going, like, how do you do your job every day? And I can then codify that into rules. I can ultimately try to help you out with your job or automate you away. How do I build some system that can interact with people to acquire the knowledge from them and ultimately store that into some knowledge base? Now, why add KRR to machine learning? This is likely helpful for everyone in the room. One is explainability. So what's interesting is, as I described it to my mom, knowledge representation and reasoning is kind of coming from the top down, and machine learning is coming from the bottom up. So if you use some machine learning technique, say to classify a cat picture, which is always a classic Google classification, it may trigger on features that are not observable to us, right? But as human beings, we've developed this thing called language, which is a level of abstraction to communicate to each other some underlying complexity about this natural world, right? And as knowledge representation and reasoning, we start with kind of these higher level abstractions and try to come down to these very specific granular pieces, whereas machine learning kind of goes the other way. So with knowledge representation and reasoning, as you're able to take the very low-level features of your data and map that back to a higher level abstraction, well, then now you can communicate with humans more effectively. The other is the prediction step. So there's all types of reasoning. There's 4, I believe: inductive, deductive, abductive, and analogical. And statistical inferencing is a very powerful technique, but there are other approaches to reasoning. And to be able to bring in other reasoners into your machine learning models could actually be very helpful. But then the target of machine learning is actually representation. And to not have some formal representation to then reason over, I think is a waste of time and resources, in the sense that if you can really machine learn knowledge from data, and that knowledge representation can then be used for other tasks, I can then transfer knowledge from this trained model to some other technique, right? So it's like, look, if I learned chemistry in college and I leave college, I can then use that knowledge that I learned in other problems that weren't in my textbook, but I'm knowledgeable now about chemistry. Whereas with machine learning, you actually may not be able to transfer that over. And then, of course, I believe getting business value from machine learning requires reasoning for analysis and decisions. So what's interesting is knowledge graphs are becoming extremely popular within the enterprise. I'm not sure if people are familiar with knowledge graphs, but they are getting broad adoption across the Fortune 500 companies for all types of search, discovery, analysis of data. And if you can use machine learning to help you build those knowledge graphs, then you can actually get a lot of value. I'll actually just stop real quick. So my advice, and this is something that I actually tell my researchers, is learn as much as you can and don't discriminate. And what I mean by that is a lot of folks, whether you're in the machine learning camp or you're in the knowledge representation and reasoning camp, try to use their techniques to solve every problem. They have a hammer and everything is a nail. And it's really frustrating sometimes to see that. And you want to start with the problem, and then look at your toolbox and see what tools you have to address that problem, and choose the best tool for that problem. Yeah. So I've seen a lot of researchers really get hung up on trying to use a technique that is phenomenal at image classification to do open-ended question answering, right? So it's learn as much as you can. Don't discriminate against certain types or different camps, and learn to use all the tools in the AI toolbox. And if I left you with anything, I'm hoping people are walking away going, I'm an expert, or at least getting there, in machine learning and statistical techniques. There's this entire field of knowledge representation and reasoning that could further your career. And actually, I think that's coming down the pipeline with a lot of the research that you do. So apparently my time's up. Thank you.
We have time for about one quick question.
Okay. Which one? I'm not going to choose.
Biology?
Yeah.
Let's go all the way in the back.
Okay, so you just blew my mind. So I used to work as a faculty in radiology at the University of Arizona. The problem we had there is that we tried to combine some of the knowledge of the radiologists and their notes with the machine learning thing, but I left that job because I had a data size problem. So I didn't have enough cases. It was really expensive to acquire data. So how much data do you need for this knowledge representation and research?
Yes, so that's the challenge for both. So not much if you can acquire the knowledge from the human being.
Correct.
Yeah. So a lot of times you can talk to subject matter experts, and you can get that knowledge from them. We at Kyndi have, and this is actually the challenge in fusing those two approaches together, is you actually have to come up with a new data representation to be able to machine learn representations from data. We actually borrow a lot from quantum physics and treat things as kind of these field models that it's a long story. But anyway, you're able to learn from very small amounts of data now, and then use that knowledge representation that you acquire then go over to a new field. So just to kind of one last point here is that I think a lot of folks in machine learning also don't understand that the tagging of images is the accumulation of knowledge.
Sure.
Yeah, right. And a lot of folks in machine learning will say, all right, you now need to go talk to subject matter experts to acquire your knowledge. And then the knowledge representation reasoning folks will say, well, you got to go get 10 billion liquid photos. So yeah, it's not many. You don't need much data to train your knowledge system, but you do need to interact with subject matter experts.
Awesome. Thank you so much, Ryan.